In this lab, we are going to determine the gas law constant value through experimentation.
By Anubhav&Yuta Okada. What is the gas law constant? Well, in your chemistry classes, your teacher might say use the value 0.0821 liters atm per mole degree Kelvin whenever you see the letter R in your gas law equation. Some of you may think it's magic or like some really complicated experimentation, but the experimentation used is actually quite simple. And this R value is extremely important because it's used in the ideal gas law equation as well as the van der Waals equation, which we will get to later in the presentation. It's used in the equation PV equals nRT repeatedly in order to find either the volume, pressure, temperature, or the moles of gas in question based on other values that are given. Once again, this lab will determine what the gas law constant is through experimentation, and we will use a pretty simple setup to measure this. The two gas law equations that we're going to use are PV equals nRT, which is the ideal gas law equation, and the van der Waals equation on the right. Now, not all gases behave in ideal behavior. As a matter of fact, none of them do. Some are more ideal than others. Now, PV equals nRT does not take this fact into account. It does not take into account what type of gas is being used. It just assumes that the gas takes up no volume and is not attracted to anything. Therefore, the equation on the right is far more sophisticated. As you can see, it has two main differences from the ideal gas law equation. For one, it uses n squared A over V squared added to pressure, and it subtracts NB from volume. Now you may be asking, what are these values? What are all these constants? There's only two constants, A and B, and these depend on the identity of the gas in question. The value n squared A over V squared takes into account the change in pressure based on the gas. The value NB takes into account the amount of space the specific gas takes up, because a mole of gas doesn't take up no volume. The gas particles do have a certain amount of volume, and this is equal to nRT. Now, we can't just determine the R value. What we have to determine are all of the other four values, and through that we can calculate N, because R is just a ratio of the changes in pressure and volume and the changes in the amount and the temperature. And we're going to have to use these gas law equations to calculate it. Here's our setup. It may look a little complicated at first, but it's not that hard. What we're doing is heating up some sodium chlorate with manganese oxide in order to produce oxygen gas. This gas is going to displace water, and we're going to measure exactly how much water was displaced. Now, here are the key facts. The sodium chlorate and manganese oxide, they're very small amounts. In fact, it's 0.3 grams. Therefore, it is important to precisely measure as accurately as possible the volumes throughout the lab. Now, this lab is very good because it also teaches students what a catalyst is. Manganese oxide is not used in this reaction. It does not react. It simply helps speed up the decomposition of sodium chlorate to produce oxygen gas. Another key safety feature that this lab will teach, which we learned the hard way, is do not put a flame over chemicals. It is important to heat up chemicals indirectly by having the flame skewed a bit so it does not point directly at the chemicals which are being heated. Now, basically, you're going to produce oxygen gas in the test tube, which is going to be transferred into a flask. There's two tubes in the flask. One is connected to a beaker and one is connected to the test tube. Now, this is a little bit more sophisticated than it looks, because in order to achieve atmospheric pressure inside the test tube and inside the flask, we need to create an equilibrium between the beaker on the right and the flask on the left. The way we do that is we fill up both of them around halfway with water, and then using a rubber bulb, we blow in air through the tube on the left in order to fill the tube on the right with water. We clamp off the rubber end on the tube on the right until we receive an equal level of water in both the flask and in the beaker. Once these levels are equal, it means that the pressures inside are also equal, and then we can run our experiment. And as you can see, it looks like we're just measuring the volume of water that's being displaced. I mean, one can just put it in a graduated cylinder and guess how much water it was. But that is not precise. Our lab needs to be as accurate as possible with as many significant figures. And the correct way to obtain that is to determine the volume based on mass and density. Now, your teachers may tell you, ooh, the density of water is 1 gram per milliliter, which is true, but density also is dependent on temperature. The hotter the liquid, the lower the density, and vice versa. Therefore, this lab will teach students how to take temperature into account as well, because we're going to have to measure the temperature of the water not only for the vapor pressure, which I will get to in a few seconds, but also to determine what the exact density is. We can calculate the mass of the beaker after and before the experiment, subtract the two to calculate the mass of the water displaced, and then use density to find the volume, which will be the volume of oxygen. Now you may be thinking, how will we figure out how much oxygen we used? This is actually very simple. We're going to take the mass of the chemicals in the test tube before the reaction and the chemicals in the test tube after the reaction, because the only thing that should go away is the oxygen. The NaCl in sodium chlorate just becomes salt. It is also very important to know that the sodium chlorate doesn't all decompose. As a matter of fact, in our labs, less than 20% decomposed, which means you still have sodium chlorate in the test tube, and sodium chlorate is very toxic, so we learned safety procedures of how to deal with that, which I will get to later. Now, as the air goes into the flask in the middle, you may think, okay, so it's going into a liquid, so technically the only pressure that's being exerted is the pressure by the air, which is being funneled in. Now, this is not the case, because this lab teaches kids the importance of vapor pressure and partial pressures. Because, as a matter of fact, the atmospheric pressure is not equal to the pressure of the gas. In fact, the atmospheric pressure is slightly higher, because water does exert a pressure. Even though it's a liquid, there are molecules of water that are escaping the liquid state and becoming a gas. And this is why we need to take into account the vapor pressure of water. And the way to do that is to use a chart which depends on water and the temperature of the water. So now we know the pressure of the gas, we know the amount of gas, and we know the volume of the oxygen that was produced. So what's the fourth letter remaining? T, temperature. This is very sensitive, this reaction, because if you heat up the tube too fast, then the actual temperature of the gas will be much higher than the temperature of the surroundings. This can create a problem, because if you have a higher temperature than you recorded, then your R value, your gas constant, will be much higher after you calculate it than what you expect it to be. Therefore, I cannot emphasize for safety, for everything, how important it is not to heat up the sodium chlorate directly. This is how the lab actually looks like once you set it up. It's not as pretty as in the diagram, but I mean, it still works, and it teaches students how to use glass tubing, create seals, and use stoppers. Also shows students why you need to, for example, angle the test tube sideways, because you don't want to end up burning the rubber stopper on the top. So this lab teaches students how to handle a variety of important lab materials. Additionally, we'll learn how to use a Bunsen burner properly so it doesn't produce a narrow stream but rather spreads out, so you get like a steady yet not too hot flame. So why do this lab? I mean, why is this important? Because the procedure is not too difficult. It's pretty simple. We just measure 4 things: the volume, the amount of moles of oxygen, the temperature, and the pressure. And all that we need to do is perform calculations after that. Additionally, this lab is very important because it gets all those careless students who forget to cancel their units and change them properly, it gets them to mess up. And through that, they'll realize how important it is to pay attention if it's inches of mercury, millimeters of mercury, ATM. Because all 3 are used in this lab. Not all barometers are the same. Additionally, There are going to be other situations where units will need to be changed from Celsius to Kelvin, as well as milliliters to liters. The equipment that we use in this lab is not too high-tech. Apart from the mass balance, which needs to be very precise, everything is readily available. And the chemicals that we use, sodium chlorate and manganese oxide, are also very common and inexpensive chemicals. They're not like chloroauric acid, which costs $100 a gram. These are pretty cheap, so teachers can spare students who mess up. And it's not too difficult for students to properly complete, and it doesn't require too much time. The lab is pretty simple and it's fast if you do it properly. And having a teacher help set up the demo helps out the students because all they need to do in a sense is copy it. And this teaches students what some flaws may be in using an idiometer to measure volume of gas, because an idiometer is much simpler. I mean, all you do is fill up a tube of water, flip it over a bigger tube of water, and measure what happens when gas goes in the smaller tube of water and how much the volume changes, and all you have to do is read. But that is inaccurate, and this shows how different ways of measuring can give much more accurate and better results, and the simplest way is not always the best way. Therefore, this teaches students how to be precise. It's important to get that extra zero in your math, even if it requires you running on the other side of the room to use the proper weighing mass balance. Therefore, the students will learn a variety of techniques which will help them not only in this lab but later on. The most important thing, however, that students will learn in this lab is the gas law. They will learn exactly how a change in one variable can affect any of the other three variables. Using the simple equation PV equals nRT and saying, oh, an increase in pressure causes a decrease in volume can be memorized. But running this lab will actually show students that it happens and it's not just an enigma. So what do we expect of the students? Well, we expect them to know the ideal gas law and the van der Waals equation. Now, they don't need to memorize all the values of gases in the equation, all the AB values, because that's not even physically possible. It's just important to know that the gases, they do not follow the ideal law. And if we wanted to make this experiment as perfect as possible, we would be running it at around 1000 Kelvin, getting it as hot as we can, and at the lowest possible pressure, because that's when gases behave totally ideally. But yet we cannot do that, so we have to use what we can do and just try to figure out how close we can get. After running this experiment ourselves, we learned a couple of things. We went from having a 90% error to having just 1.34% error. The way we change this is by heating up the gas much more slowly, because this did not increase the measured temperature. Once we did this, we did not have a false positive. So students will learn that by actually working slower and being more careful, the results can be much more precise, even if the data is as sensitive as it is in this case, because 0.0821 is a number which can change very easily with just a small slip of the mass scale. It also teaches students how to use proper math techniques, because running the whole PV equals nRT van der Waals equation, converting all the units, is a little time consuming, and it shows students how to use stoichiometry, how to properly figure out how much volume is being displaced, and they also learn stuff about partial pressures and vapor pressures, so it's very useful. And they also learn how to complete an experiment as accurately as possible. In this experiment, our average percent error was 35%, which in a chemistry lab is very good. We're used to seeing 300% errors, so a 35% error definitely shows us that this lab is workable. I mean, if students run this lab and get values that are off by just a third of what they're supposed to be, that means they're doing something right, and it means that they're getting close to what they actually need to get to. Now, all our values were higher than expected, which is because we heated it up, but if students have all the time and run fewer trials and make them much more accurate and take care, I'm sure they can receive as low error as possible, and they can avoid the frustration of having incorrect data, as people sometimes see in stoichiometry labs with combustion, where percent errors seem like numbers on the readout of an airplane speed. Once again, we would love to have students run this lab because it teaches them how to use the gas law, how to be careful with their units. They learn about pressures, they learn about the gas law through experimentation, which means they actually see what happens when something changes, not just write it down. And lastly, they'll have a good time because it is really fun to watch gas bubble the water and go inside another tube. It looks much more complicated than it is, and it's very fun. Thank you for listening to this presentation.